So now we're just going to look at a couple examples. We're going to look at a carbon dating example and just a generic exponential function. So let's look at this one. So let's say that a parchment fragment was discovered and it had about 74% as much C14 radioactivity as plant material on the Earth today. So estimate the age of the parchment. So we're going to say that the amount present, or the initial amount, I mean, this is the ratio. This is, still have it up here. This is the ratio of C14 to C12. So that's the initial amount because that's as long as things are alive, that's what the ratio is. So we're going to use this for our initial amount. Then the current amount is 74% of that. So the current amount is this. And then we can just solve for T. So we can divide both sides by the ratio of C14 to C12 in the atmosphere. We wind up with this. Take the natural log of both sides. We get this. And then we still need to find out what K is, but remember the half-life time for C14 is about 5,730 years. So we can use this formula, solve for K, and you get this. So this is the K, the constant K for C14. And if we go ahead and just plug that K, this value into this formula, you wind up with this. So the parchment's about 2,500 years old. So that's an example of using the carbon dating. And then here's just another example that we'll do. So let's say the intensity of light passing through an absorbing medium decreases exponentially with the distance traveled. Suppose the decay constant for a certain plastic block is 4 meters to the negative 1. How thick must the block be to reduce the intensity by a factor of 1/3? So again, we're going to start with this. It is exponential decay. So we're going to use the one with a negative. And we want it to have 1/3 present left. And so we'll go ahead and work it out. And we get this. And by the way, you may have noticed, if you watch the doubling time half-life formula, I mentioned it very quickly at the end, but I talked about how doubling time is the natural log of 2 over K. So tripling time would be the natural log of 3 over K. And then just like half-life, it's the same formula for half-life. It would be the same formula for uh, 30. I don't really know what we would call it, but you can see it right here. There it is. So if you knew that, you could jump down to here. But if you didn't know it, you can start right from the very beginning. And so that would be the thickness needed for the plastic. Anyway, that's just some examples. You don't have too much homework, so have fun with it. And I will see you guys later. Bye.